Okay, hello. So I've gotten quite a few questions about this problem in general, and it's a pretty hard problem, so it makes sense. So first thing I want to do is, you'll see I already have some stuff written out. That's because the video where I had stuff going in real time was a little bit long. So we have our molar mass given to us here, and this is of the acid. We have our octanol water coefficient here, and that's going to be important in the next step. And we also have a Ka value. So we know that our acid is weak. Okay, so from here, I want you to recall that the formula for concentration is C equals N over V, N equals M over M, and consequently moles equals M over M. And our moles were given by 2 grams over the molar mass, which is 0.02 moles because units cancel out, but you can do that with dimensional analysis. And our KOW is equal to concentration in octanol over concentration in water. The KOW is a ratio between the amount dissolved in water and the amount dissolved in octanol. It's a ratio between how much dissolves, but it dissolves equally into both. And that's really important. So try to wrap your head around that. And I replaced the concentration with its formula here, N over V, so you can see what's going on. And we know the initial amount of moles, right? But we don't know how much of it ends up in the octanol and how much of it ends up in the water. Equal amounts will end up, but we don't know how much of it disperses, right? So this is basically me skipping a step from ice tables. You can do an ice table with, I guess, octanol and water. And you can, set up an ice table. This is minus x, and this is x, right? And it's all going to be 0 over 0.1 liters because the concentration was 100 milliliters, which is 0.1 liters. And, it'll look like that, the ice table. But the ice table really is not necessary here because it's just one plug into a formula. So we plug this into a formula here, and then we notice that they're both in 0.1 liters of concentration. So what I do is I get rid of the denominator in the top and bottom to simplify our fraction into this. Now, a really important note here is people ask me, why don't I set the 0.02 to the initial amounts? Why don't I set this to 0.02 minus x instead of the top? And the answer is I could, but it makes it easier to simplify if I put the x in the bottom. It actually will give you the exact same answer because these two should end up being equivalent because equal amounts disperse in both. Okay, so from here, we set all of this equal to the KOW, right? And our given KOW was 5.6 right here. So 5.6 equals this equation, and this is where having x in the denominator is really favorable to us because we multiply x on both sides, and we get 5.6x on this side, and then this side's denominator disappears. But I also brought over the x in this step here, just because I wanted to do it in one step. So now we have 5.6x plus 1x on the left and 0.02 on the right. I'm going to let you look at this for a second, make sure you understand how I isolated for the x there. And from here, I just divide both sides by its coefficient, 6.6, to isolate the x completely, and I get 0.02 over 6.6. And this gives me 3.03, approximately 3.03 times 10 to the power of negative 3 moles. We want to further divide this by 0.1 liters. Why is that? Well, we got the moles of what's in the water, right? But we simplified it earlier, and we got rid of the concentration. So we just solved for moles, but we didn't actually get the concentration. But the concentration is still 0.1 liters. So we divided by a further 0.1 liters, and this gives us 0.0303, or 3.03 times 10 to the power of negative 2. So we've essentially increased our degree by 1. Okay? And I wrote the little C equals N over V here so you understand why we're doing that. All right, so let's do it from here. From here, I set up an ice table, right? Because I now have the concentration of what's in my acid, like my amount of acid in water, right? It's equal amounts, right? But for this one, I'm looking for what's in water. So I have the concentration of what's in water now. So I have my initial value, okay? Because there's two equilibrium processes, right? It's like it equally disperses, and then what's the pH in the water, right? So it says right here, consider the equilibrium process to be sequential and unrelated chemically. So that simplifies it for us, okay? So you can see my ice table set up here. So this is the initial amount. So we have none of water because this is a liquid, and we don't include it in our equilibrium calculations. This is our acid, and we calculated the initial amount here. The change is going to be minus x, and all the coefficients are 1, because if you recall from class, acid base, not for bases always, but for acids, it's usually just going to be 1 because they're monoproduct. And here we have our Ka, right? Ka equals x squared over the products or reactants. And for here, we want to try to simplify it, right? We want to divide our initial value by the Ka to see if it's greater than 100. If it's greater than 100, our simplification assumption is valid. But you see I write it's invalid here. That's because this doesn't give me something greater than 100. If I plug it into my calculator, it gives me, actually forget what it gives me. It's going to be 0.303 divided by 2.7 times 10 to the power of -2 times 10. It gives me 1, right? Which is a lot less than 100. So our simplified assumption is invalid. Okay, so we go back here, and we know we have to solve this like a quadratic formula, right? So we first have to set our calculator into quadratic mode. There are instructions for it on the slideshow. I'm not going to do it here. But here we have x squared plus, and then we're going to distribute this term into the brackets, right? So we have x squared. Actually, I'll show it to you here. So these two terms become 2.7 times 10 to the power of -2 negative x, and 2.7 times 10 to the power of -2 times 0.0303 is our C value, right? Because quadratics come in ax squared plus bx squared plus c. So this is our C value. This is our B value. And 1 is our A value. But we have to make it all on one side of the equation first, right? So our B value becomes positive 2.7 times 10 to the power of -2x, right? Let's just put this in brackets so no one's confused. And then our C value becomes negative because we've brought it over to the other side, right? Minus, we're going to put this in big brackets, 2.7 times 10 to the power of -2 times 0.0303 equals 0, right? So this is our C, this is our B, and this is our A. And it's really important that you use the correct signs, because if you don't use the correct signs, you'll get a completely different answer. That is the nature of math. But our C value is negative here, right? And our other two are positive. So we can just plug them in as is. So my calculator is prompting me for the A value once I set it up, so I give it 1. The B value will be 2.7 times 10 to the power of -2. And my C value would be negative 2.7 times 10 to the power of -2 times 0.0303. So my first x value is, my x1 is 0.018, and my x2 is negative 0.045, okay? Now, I look at this, and I'm like, well, my x can't be negative. I can't have a negative concentration. So the only valid one must be 0.018, right? So from here, I'll set my calculator back into its normal mode. And here I can do, I can find what my x is, right? It's actually just 0.018, so I didn't have to subtract anything, right? So the concentration of hydronium ions is 0.018. Cool. So it's asking me for the pH. Well, the pH is equal to negative log of hydronium ions, which is equal to negative log of 0.018. So let's do that. Negative log of 0.018 equals. And this gives me approximately 1.74. That's our pH value. And we see if we have a matching value, which we do. So we're done. The pH value is 1.74.